Okay, so to start out with, it's going to end up being kind of a little bit of a review of kind of some of the notes yesterday before we get into examples. But anyways, for Bernoulli trials, there are two possible outcomes. We either have success, P, or failure, Q, and Q is equal to 1 minus P. The probability of success always stays the same. And trials are independent. So some examples of Bernoulli trials would be something like flipping a coin, because you either get heads or tails, so that's your two possible outcomes. Free throws in basketball. You either make or you miss. Or something like looking for a defective product. On an assembly line. The geometric model is modeling the number of Bernoulli trials until the first success. The 10% condition in geometric models trials aren't independent. Since we are sampling without replacement. As long as our sample is less than 10% of the population, we can assume they are essentially independent. So some of these problems I will show you, like if you were to do them by hand, and then also like if you have a calculator, what the calculator function is for them. Because there's part of the AP exam that is with a calculator and part that's without, and this is one of the topics that can show up on either part. So that way you know, like, okay, here's how I do it by hand. It's not hard by hand, it's just, time consuming. So suppose a computer manufacturer rejects 2% of the chips produced because they fail pre-sale testing. What's the probability that the fifth chip is the first bad one that you find? So we're looking at the probability of bad which is 2%, so that's equal to 0.02. Trials aren't independent. And this isn't all necessarily stuff that you would need to actually write. I'm just writing it more for reference for you. Trials aren't independent, but 5 chips are less than 10% of all chips manufactured. So I'm going to basically treat it as if it is independent because of that 10% condition. So the by hand way to do this is the probability for x being equal to 5. So we're looking at the 5th chip is the first bad one, which is, even though it's bad, it's our success because that's what we're looking for. So we're using the geometric model. So this is going to be from the formulas we had yesterday. 0.98 to the 4th, so that's a failure because we want the first success, bad one, to be the 5th one. So 0.98 raised to the 4th times 0.02, and that would be equal to 0.018 or 1.8%. Then the calculator way to do it, we're looking at geometric PDF. So it's GEOMET PDF. And then it's going to ask you for P comma N, which is, if you were to type it in, it's geometric PDF of, in this case, 0.02, because it's going to be your success. And then the number that we're looking at, which is 5. So I'm going to give you this so you can do it. But you just hit second and then bars, and then you'll just arrow down, or you can arrow up because it's going to be the ones at the very bottom. But it'll look just like that. And that's also where the binom one that we'll use is as well. It won't show it to you in parentheses. It'll actually ask you for like P and N, or it'll say like probability in trials or something like that. And you just type it in. Did you get it? Same thing? Yeah, so either way, basically all I'm doing is showing you that you get the same thing no matter which method you use. So PDF is the one where you care about the order. It's like the first 4 you don't get, and then you get the success on the 5th one. So then the next one, what's the probability that you find a bad one within the first 10 you examine? So we don't care about, like, it doesn't have to be like, oh, number 7 is the bad one. It just, in this group of them, one of them has to be bad. So again, I'll show you the by hand and then I'll show you the calculator. So we're basically looking for the probability that is between 1 and 10. Now, it's really long, so I'm not going to write out the whole thing. I'll do like a ... but the probability of success on the first one would be 0.02, meaning that there was no bad ones, plus the probability of a failure on the first one, the second one being a success, so it would be plus 0.98 raised to the 1 times 0.02 raised to the 1. And no, you don't have to write it. I'm just writing it for the sake of you seeing what I'm doing. Plus 2 failures, then a success, so it would be 0.98 squared times 0.02 to the first, plus ... all the way out to the last one, which means that if the 10th one is the first bad one, we had 9 good ones. So 0.98 to the 9th times 0.02. So you could obviously type all that out, solve it, blah, blah, blah. I personally wouldn't because that's a lot. So you can use still geometric. So geometric CDF, which is cumulative. So you still do 0.02. We're running 10 trials. And another thing we could have also done, I'll just write down here, is we could have also done 1 minus the probability of no bad in 10. So we could have done 1 minus 0.98. Or not 1 minus 0.98, but 1 minus 0.98 to the 10th. Or something like that. Anyways.
I got
0.017? With this typed in? That's not what I have it should be, but that I could have it written down wrong. Check. I have that it should be 0.183-ish, but that could also be wrong. I could have had it written down wrong.
Oh, I did PDF, says CDF.
Oh, yep, that'll do it.
I said I got an error. Hold on.
Would you get 0.183? Okay. Okay, so then that's all in that one. Okay, so an Olympic archer is able to hit the bullseye 80% of the time. Assume each shot is independent. If she shoots 6 arrows, what is the probability of each of the following results? So the first one is that her first bullseye comes on the 3rd arrow. So that means the first 2 were misses, and then we had the make. So we're looking at the probability for x being equal to 3, which is going to be 0.2, which is the failure squared because she shot 2 and missed. And then the make times 0.8. And so you can either do it this way or calculator, which is what I would do, is geometric PDF because we care about the misses and then the make being on a specific one. So geometric PDF of the success, which is 0.8, and 3 for the one that she makes. And so then you can run that. 0.032. So then she misses the bullseye at least once. At least says that I should look at what?
Huh?
The words at least. If it says to do something at least whatever. What did we say yesterday that we should use? I think it was like one of the last things we put in the notes.
Says at least 10% condition.
It says something about when you see the words at least think this or something like that. Starts with a C. I'm pretty sure we wrote it and I didn't just say it, but I could be wrong.
Binomial.
No, compliment.
Uh,
So we're going to look at this as if it is 1 minus the probability of never missing. Because missing at least once could mean she misses 1, 2, 3, 4. So it means she can miss all of them potentially. So we're going to take it off of the probability that she doesn't miss at all. So that would be 1 minus 0.8 raised to the 6th. Which you could do that way. Or the other option, we could do calculator. 1 minus binomial PDF. And it would be, I can't remember exactly what order it gets. I know what order it gets written in, but I can't remember what it asks in the prompts are. But it would be 6.8 and 6. So one of them is like the number of trials or something. I can't remember exactly what it is. You'll see it when you put it up there. But it'll be 6.8, which is the probability, and then 6 again. So if you do 1 minus that, and you get that function the same way you get to the geometric one, then that gives you 1 minus whatever that number is. So you can just type in 1 minus and then go find the function and do it.
you got 0.738.
Yep. All right, so then her first bullseye comes on the 4th or the 5th arrow. So that means that we could have 3 misses and then a make, or we have 4 misses and then a make. So we can look at this 2 ways. We can look at this as the probability for x being equal to 4 plus the probability for x being equal to 5, which is 0.2 cubed, so that's the misses, and then a make of 0.8 plus 0.2 to the 4th for 4 misses, and then 0.8 for the make. So you can do that by hand. Or if you still wanted to use the calculator, we would still set it up like we did this geometric PDF here, but now we're adding the 2 things together. So you would have geometric PDF of 0.8, and it comes on the 4th one, plus geometric PDF of 0.8 and 5. And if you type in geometric PDF and then type it in and then hit the plus sign and then do the other one, it should let you do it all as one big strand. But if not, you can do each individual piece. Huh?
I'm about to plug in. So the first one is 0.006. Second one is 0.00.
So then that ends up being 0.007, right? And then the next one, she gets exactly 4 bullseyes. So that means that out of the 6 shots, she gets 4 of them. But we don't care in what order. We don't care if she does 4 bullseyes, then 2 misses, 2 misses, then 4 bullseye, a miss, 4 bullseyes, then another miss. Like, we don't care how it happens. So we're using combinations to set this up. So it'll be 6C4, which means the number of ways she can make 4 out of 6. Because quite frankly, you're not going to want to sit and figure that out by hand. Like, you could list out all possible options if you were just so inclined, but that would take a long time, especially with bigger numbers. So we have that. And then times, we want her to have 4 makes, so 0.8 to the 4th. And then 2 misses, 0.2 squared. And if we multiply all that together, it'll come out and give you some number. To find this function, you have to type in, or you have to go to math and then arrow over to PRB for probability, and then you'll see one that's written as NCR. And I never remember, you may have to, when you do it, it may take your previous answer as your N value, so you'll have to replace it with 6. Also, sometimes this gets written like this with numbers stacked on top of each other, almost like a fraction without a fraction bar. So if you see it written like that, that means the same thing.
So I uploaded in the combination.
So did you find the function? So you'll type in, so like you may have to arrow over, because do you see A and S?
A and S.
Like, is it currently written like this?
Yeah.
So you'll have to just go arrow to the left and replace this with 6. It takes whatever, so sometimes they're assuming you've already typed the number in before you ever hit the thing, but I never do that, so I always just arrow over and basically replace that with the number 6, and then arrow to the right and replace that with the number 4. And then you can just hit enter if you want, and that'll tell you how many possible combinations or how many ways she can get 4 bullseyes taking 6 shots.
I got 15.
So that'll be 15, and then you could obviously multiply that out and get an answer, and that's the by hand way. But of course, there's a calculator way that can do the whole problem for you. And so binomial PDF, because that means an exact amount that she gets. So binomial PDF of 6. So it's 6 trials, successive 0.8, and then she wants 4 successes. And then whatever that equals. should be equal to the same thing if you actually multiplied this whole top equation out.
At
0.246. So then the probability that she gets at least 4 bullseyes. So at least 4 would mean she can get 4, she can get 5, or she can get 6. So there's, again, a couple ways we can do this. We can either find the probability that she gets 4, plus the probability she gets 5, plus the probability that she gets 6, which is how you would have to do it by hand. Or, well, that would be the easiest way to do it by hand. Or we can do it the calculator way, so I'll, again, show you both. But, so this is 4, 5, or 6 bullseyes. So we would have 6 things taken 4 at a time, so that's the same way. So this would be like 6C4 still. Times getting 4, so 0.8 raised to the 4th, and then 2 misses, so 0.2 squared, plus 6 shots, taken 5 at a time, so this would be 6C5, times 8 makes, so 0.8 raised to the 5th, times 1 miss, so 0.2, plus 6 things taken 6 at a time, or 6C6, and then times 0.8 raised to the 6th, because she made all of them, so there's no misses that it's being multiplied by. And you can multiply that out, blah, blah, blah. And just something to note is that they did not specify an order. It didn't matter if she got, 2, then missed, then got 2 more, and then missed, or whatever. So since no order was specified, we're using binomial. So if order matters, it's geometric. If order doesn't matter, it's binomial. So we can also do this as 1 minus the binomial CDF, because we care about 3 different options. So binomial CDF of 6, so how many trials, the probability of success, and then 3, which would mean 3 of them that were missed. So 1 minus that would account for 4, 5, and 6. Otherwise, you have to do them all individually, because this will add up everything 0 to 3, so it'll subtract that off.
I got 0.918.
0.918. All right, and then the last one for this problem, she gets at most 4 bullseyes. So that means she gets 0, 1, 2, 3, or 4. But she doesn't get more than that. So we have a couple options. By hand, we can do 1 minus the probability that she gets x is equal to 5 or x is equal to 6 and add them together.
Could we just subtract 1 from you get the answer?
No. Because this was that she got 4, 5, or 6. This is that she gets at most 4. So if we hadn't done 4 up here, yes. So basically, it's 1 minus this stuff right here. So it's 1 minus this part. So I'm not going to rewrite that again, because the calculator's, again, easier. So now, remember, binomial CDF adds up everything up to that point. So I don't need to do 1 minus since I only care about 0 to 4. If I cared about 5 and 6, I would have to subtract 1 minus 0 to 4. I care about 0 to 4, so this time I don't need to subtract. So binom CDF 6.8 and 4, and that's going to give me the value that I'm looking for. Is it dead?
No. Anytime I want to reset a calculator, I just take the battery out.
Oh.
That 0.246.
0.246.
Oh, wait, hold on. I just PDF again.
Okay, I was like, it's not what I had on my paper, but again, that's not necessarily meaning that I did it right, so. Or that the numbers that I have on my paper are right, because I haven't used paper in a while, so I could have hit the wrong button or something.
All right.
Okay, that's what I thought it should be. Alright, we'll go ahead and start the next one. We probably will get through it, but if not, we'll just pick it up tomorrow. Alright, so about 8% of males are colorblind. Are you colorblind? Okay. One of my really good friends is colorblind. So, anyways, I just think it's fascinating. I never understood what it was like to be colorblind until I was doing a colorblind test with him one time. And I was like, oh, he, like, actually is colorblind.
I do just say different colors.
Yeah, so, like, red will look like green, yellow looks like orange, like, blue looks like purple.
Oh, okay.
So, like, basically there's this thing, Miss Marshall has it, but I don't think she uses it, but, like, I use it in physics when we talk about color. But more so just for fun. But basically it gives you, like, 20 pipe cleaners attached to, like, a cardboard backing, and then you have a bag of pipe cleaners and you have to match them up. So it's really funny because what I didn't understand about people that are colorblind is that in some cases they can't even tell that two things match, even when put side by side. So anyways, that's what I was saying. I didn't really understand it until I started looking at it more and like, oh, that's like actually a thing. Like, I don't know. I kind of thought it was a myth, but it's not. So anyways, I just always like to find out if anybody in the class is colorblind. It's more common for guys than girls to be colorblind, so at least from what I understand, but I'm not a scientist, so. Anyways, a researcher needs some colorblind subjects for an experiment and begins checking potential subjects. What's the probability that she won't find anyone colorblind among the first 4 men she checks? So a success is that they are colorblind, which would be 0.08. So no one is colorblind. We're using failure. So that would be 0.92 raised to the 4th. And I would just do that in your calculator. It's going to be easier than doing any of the other functions. multiply that for me? It's just easier than using the other functions when you're just doing something like that. Just multiply it.
0.716.
Yep, 0.716. So then, what is the probability that the first colorblind man will be the sixth person checked? So, again, we can do this by hand or calculator. So, by hand, the probability for x being equal to 6. So, we have 5 failures, then a success. So, 0.92 raised to the 5th times 0.08. Or geometric PDF for, I always forget what order it goes on when it's not in front of me. 0.08 and 6, I think, is the order. But I might have that backwards. I don't have it in front of me, and I don't have these ones written out on my paper for the calculator function, so. Because honestly, sometimes rather than going and finding the calculator function, I'll just go ahead and multiply it. You get the same answer either way, so. But I usually try to show both just to make it easier. I was looking at the wrong problem. I was about to tell you that was the wrong answer. All right, so then what's the probability that she finds someone who is colorblind before checking the 10th man? So that means that we care about 1 to 9 because we want to see if she finds someone that's colorblind before she gets to 10. So this is the probability for 1 less than or equal to x less than or equal to 9. Suggestions on which function to use, because this one by hand would be awful, so I'm not even going to do it by hand. Well, first of all, does order matter?
You said what?
Does order matter?
No. Because then you multiply it.
Let me rephrase. Does order matter in terms of which person is colorblind?
Yeah.
Okay, yes. So what function does that mean that I need? Yeah, geometric, and then I care about 1 through 9. So is that PDF or CDF? Yep. So geometric CDF of 0.08 and then 9 because we care about up through 9. .528. All right, and then on average, how many men should the researcher expect to check to find someone who is colorblind? So this is the expected value for this is the formula 1 over P. So P is success. We said that 8% of males are colorblind, so that's 1 divided by 0.08. And that's what? I'll tell you, it's not a whole number, if that helps. Yep. Look at you go. I don't have patience for that. So basically, if it were to ask you, like, kind of a conclusion for that, she will have to check. Now, she will have to check 12 and a half men, but you can't have a half a person. So,
About 13.
yeah, I would say about 13 men before finding a colorblind man. Have you ever watched the Andy Griffith Show?
I see bits and pieces of it.
Okay, well, so there's this one episode where Opie, the little boy, they are collecting money for, like, some drive or whatever for kids that needy children. And so, anyways, the dad ends up saying something about, like, well, it's, did you know that 3.5 boys don't have, enough food or something like that. I don't remember the exact thing. And he says, how do you have a half a boy? And he says, it's a ratio. And he says, Horatio who? Because you can't have a half a boy. And, a 5-year-old didn't understand that. So anyways, that's what I always try to use that analogy that, like, if you're doing that, I would just say about, show the math, and then say about this many, because you can't have a half a person. But it's just an expected value. That's why it's, anyways. But we'll pick this up tomorrow, because these formulas will be used in what we do tomorrow. So that way we can just review them then.